Global maxima and minima. A function is said to have a global maximum at p if f of p is greater than or equal to all values of f of x. A function is said to have a global minimum at p if f of p is less than or equal to all values of f of x. Now, this definition may sound familiar. It sounds very much like our definition for local maximums and local minimums. The key difference is this word all values. Remember, when we talked about local maximums and minimums, we talked about being near p. However, in global maximums and global minimums, we are comparing values to all values of f of x. So wherever our function is defined, every single value is considered, and we're looking for the largest dependent value to find our global maximum and our smallest dependent value to find our global minimum. A couple things to remember. So global extrema, so global maximums and minimums, are defined by their dependent value. So we're looking for the y value. So when we talk about a global maximum, if we say a global maximum is 7, that means it goes up as high as 7. So that's a y value. And if we were to say the global minimum of a function is, say, -3, that means the function goes down all the way to -3. So the way we talk about global maximums and minimums is a bit different than local maximums and minimums. Remember, with local maximums and minimums, we would report where they occurred. So we would report them by their independent or x values, whereas global maximums and minimums are reported by their y values. So functions can only have one or no global maximum or minimum. However, this can happen in multiple places. So there's either one highest value for your function or no highest value. Think of a function that goes on forever and ever, and that function will not have a highest value. Similarly, a function can only have one or no global minimum. So there's either one lowest value or no lowest value. However, you can have a function that hits the highest or lowest value in multiple places. However, there's still only one highest or lowest value. So let's take a look at a graph and see if we can visualize what we're talking about when we talk about global maximums and minimums. So looking at the picture below, we have a function that's defined from -1 until roughly 1.5. So if we're looking for global maxima or global minima, we're looking for the highest and lowest point on this function. So giving it a quick glance, the highest point happens right at the end point. So here, I can see that my global maximum is going to be 2. Remember, we're going to define these by their dependent value. So the global maximum is going to be 2, and it happens at x equals 1.5. So again, we define it by its y value, but we can also talk about where it happens if we need that information. Now, when we look for the global minimum, we're going to look at all the values here, and we're looking for the absolute lowest one, which is right about here. So that means that my global minimum, now notice here that this is a scale of 0.2 because we have 5 divisions between 0 and 1. So that means my global minimum is approximately 0.4. So again, I'm defining that by its dependent value. And I can talk about where it happens if I needed that kind of information. So this is also a 0.2 scale. So 0.2, 0.4, 0.6. So we're halfway between 0.6 and 0.8. So approximately -0.7 is where that happens. But when we talk about global maximums and minimums, again, we're looking for the highest and lowest points of a function, and we're defining them by the y value. So something really interesting happens here, and it helps set the stage for how we're going to solve and find these global maximums and minimums. There's 2 different places that global maximums and minimums can occur, and it's demonstrated here. So notice that this first value here, this global max at 2, is an end point. So my function ends here, and somehow that ended up being one of my global values. However, if I look at the global minimum, that's not an endpoint. However, it is a critical point. And it's not a coincidence that this has happened. Global maximums and minimums are always going to happen at critical points or endpoints. Now, there's two cases we have to consider here. The case where our function has some sort of endpoints and the case where it doesn't have any endpoints. So let's take a look at how we're going to define the process by which we're going to find these global maximums and global minimums. So in order to find a global maximum and minimum on an interval including endpoints, we're going to compare values of the function at all the critical points in the interval and all the endpoints. So what that means is that we're going to take every single endpoint, we're going to find where that happens in terms of the independent value, so the x values, and all the places that critical points occur in the interval that's given in terms of their x values. And then we're going to take all those and plug them back into the original function. That's going to give us the value of the function at each of those points. The largest number from that list, if you think of a number line, so the highest on the number line, is going to give us our global maximum. And the lowest value from that list is going to be the global minimum. Only values on that list are going to be considered because endpoints and critical points are the only places where we can have global maximums and minimums. If, however, we want to find a global maximum and minimum on an interval excluding endpoints, so either an open interval or if you have the entire real line, so no interval is given, it just goes on forever and ever, then we're going to again start by finding the values of the critical points. So once we have the critical points, we're going to use a picture of the function, so we'll graph the original function in some way, and determine if any of those critical points are global values. Now, if there's only one critical point, we can use the first or second derivative test to determine if that point is a global maximum or minimum. Think about what your picture might look like in this second scenario where we would need to graph it. If we had a picture that looked like this, when we do our calculations, we're going to end up with 3 critical points. And so if we're trying to figure out if one of them's a global max, a global min, etc., we need to really graph the picture to figure out what's going on. This picture does not have any global maximum because the function goes on and on forever. However, it does have a global minimum, and that's going to happen at the bottom of this first bump. There's 2 local minimums, so we would need to use the picture to determine which one was going to be lower and to actually find the corresponding y value. So that's where the picture comes in handy. Now, let's look at some examples of how we're going to compute these in various ways that we're going to look for global maximums and global minimums of different functions. Example 1. Find the global maximum and minimum of f of x equals x cubed minus 9x squared minus 48x plus 52 on the interval -5 to 11. So again, here we have a case where we have endpoints. Our function is restricted to the domain listed here, so we can only consider what's happening between x equals -5 and x equals 11. So we know that we're going to have to use those endpoints, -5 and 11, for our consideration, but we also need the critical points. So remember, we find critical points by finding where the first derivative is equal to 0. So my first derivative here is 3x squared minus 18x minus 48. And I want to know, when does that equal 0? So I'm going to factor this. So first I'm going to pull out a 3. And then I'm going to factor it a little bit further here. So I have 2 numbers that need to multiply to give me -16 and add up to give me -6. So that'll give me x minus 8, x plus 2. So again, I have 3 things multiplied together equals 0, and I need to figure out what values will make each of those pieces equal to 0. 3 will never be 0. X equals 8 will make the first parenthesis 0, and x equals negative 2 will make the second parenthesis 0. So my critical points are 8 and negative 2. So now at this point, I need to check to make sure that they're in my given interval. So I'm considering x values between negative 5 and positive 11. Both of my critical points fall within that interval, so I can use them both. So now what I need to do is I need to test each critical point as well as each endpoint in the original function. So I'm going to take f of negative 5 and f of 11. So those are my endpoints. And I'm also going to test f of 8 and f of negative 2. So again, I'm plugging each of these values back into the original function to see the y values that I get from plugging them in, because I know my global max and my global min have to happen at one of these 4 points. So when I plug in a negative 5 into my original function, I'm going to get negative 58. When I plug 11 into my original function, I get negative 234. When I plug in 8 into my original function, I get negative 396. And when I plug in a negative 2, I get positive 104. So these are the values that I'm comparing. And I'm thinking about them on a number line, which one's going to be the highest and which one's going to be the lowest. So here, my global maximum, which I'm going to notate G max, is going to be the highest value on the number line, which is 104. My global minimum is going to be the lowest number on the number line. So that's going to be negative 396. So I was able to find my global maximum and my global minimum by comparing the values of the original function at my endpoints as well as my critical points. Let's try another one. Example 2. The number h of eggs hatched by a specific insect at a given temperature T in degrees Celsius is given by h of t equals 2t cubed minus 45t squared plus 264t for t between 3 and 15. Find the temperature at which the largest number of eggs hatches. So here, we're looking for the global maximum on the interval 3 to 15. The largest number of eggs indicates that we're looking for a max here. So again, I have endpoints. So I have a restricted domain and my interval is 3 to 15. So I know already that I'm going to be testing 3 and 15 in my function. However, I also need to find any critical points and test those as well. So let's find the first derivative of this function. So my first derivative here is going to be 6t squared minus 90t plus 264. And I want to know, when does that equal 0? So if I factor out a 6, I'm left with t squared minus 15t plus 44 equals 0. And if I factor that one more time here, I'm going to get t minus 11, t minus 4. If you're not comfortable with factoring this way, you are welcome to use the quadratic formula to find the roots. So I have 3 things multiplied together equals 0. So that means that one of them has to equal 0. So 6 will never equal 0. If t equals 11, my first parenthesis equals 0. And if t equals 4, my second parenthesis equals 0. So I have 2 critical points here. T equals 11 and t equals 4. So now again, I need to take those critical points and make sure that they're in my interval. So my interval here is 3 to 15. Both of my critical points fall within my interval, so I can use them both for my test. So now again, I want to plug my endpoints and my critical points back into the original function. So my endpoints, I had 3 and I had 15. And then I'm also going to test 11 and 4. So I'm going to plug each of these numbers back into my original function to see what the corresponding y value is, or the number of eggs hatched. So if I plug in a 3, I'm going to get 441 eggs hatched. If I plug in a 15, I'm going to get 585. If I plug in an 11, I get 121. And if I plug in a 4, I'm going to get 464. So here, the global maximum is going to be 585. However, I'm looking for the temperature at which the largest number of eggs was hatched. So I'm actually looking for the independent variable here, the t value, because I want the temperature where this happens. So the 585 happened when the temperature was 15 degrees Celsius. So that's when I got my global maximum at t equals 15. If I had wanted the global minimum or the smallest number of eggs hatched, I would go to my list and I would see that 121 is my global minimum, and that happens when the temperature is 11 degrees Celsius. So let's try another example here. Example 3. Find the global maximum of the function g of x equals x over x squared plus 1 over the interval x between 0 and 2. So again, I have a restricted interval here. I'm only considering values for x between 0 and 2, and I want to find the global maximum, so the highest value that this function takes on between 0 and 2. So again, I'm going to need to use my endpoints 0 and 2, but I also need to find any critical points. So here, to find my critical points, I'm going to have to do a quotient rule. So my top function is going to be my f, and my bottom function will be my g. Now I need to find each of their respective derivatives, and I can plug that all into the quotient rule to get my first derivative of g. So I'm going to do f prime times g, so 1 times x squared plus 1, minus f times g prime, so x times 2x is 2x squared, all divided by g squared. So remember, critical points happen when your first derivative equals 0 or your first derivative is undefined. So we can consider where this equals 0 by considering where the numerator equals 0, and we can figure out where it's undefined if the denominator equals 0. So let's simplify the numerator a little bit, combining like terms so we can do easier analysis. So we have x squared plus 1 minus 2x squared. So that's going to leave me with 1 minus x squared divided by x squared plus 1 squared. Now, looking at the denominator, x squared plus 1 will never equal 0. There's nothing you can plug into x squared to ever make that 0, so there's no places where this function is undefined. However, if we look at the numerator and we consider where 1 minus x squared equals 0, we can bring the x squared term over and we get 1 equals x squared. So that means x equals plus or minus the square root of 1, which is 1. So x could be 1 or x could be negative 1, and it would satisfy this condition. However, notice that our interval is from x equals 0 to x equals 2. So that means we cannot use x equals negative 1 as a candidate for our global maximum because we're only considering what's happening between 0 and 2. So x equals 1 is the critical point we're going to use to test in our function. So again, we're now going to test the endpoints and the critical points. So g of 0, g of 2, and g of 1. We're going to plug each of those values back into the original function. So if you plug in a 0, you get 0 divided by 1, which is 0. If you plug in a 2, you get 2 over 5, so 2/5. And if you plug in a 1, you get 1 over 2, or 1/2. So looking for a global maximum means we want the largest value. So half is the largest value we get from this list. So our global maximum is 1/2. So that's the global maximum of this function on this interval. Let's look at another example. Example 4. Let g of x be a continuous function that has exactly one critical point and is in the interval -3 to -2. Find the x values at which the global maximum and global minimum occur on this interval, given that the derivative of g at -2 equals 0 and the second derivative of g at -2 equals 3. So here, we have to use the given information to figure out what we know about this function and use that information to determine how we can figure out the global maximum and the global minimum. So here, we know that g prime of -2 is 0. So that means that -2 is a critical point of this function because the first derivative is 0 at that point. Now this is important because we were told that this function has exactly one critical point. So that means that we know the place where this happened. That's the only place where the first derivative equals 0. So the only place where we would have a horizontal tangent line on this function. Now we also know that the second derivative of this function at -2 is 3. So we have the second derivative test to classify critical points, and we know exactly what's happening at this critical point. So the second derivative test tells us that if the second derivative is positive at your critical point, that critical point is a local minimum. So here, we know that this function is going to be concave up at -2. So think about what the picture of this function must look like. So at -2, we'll put -2 here. We have this minimum, right? This local minimum. And then we know that we have to be concave up, right? So since we're concave up, we have this sort of bend, which means that if we restrict this graph to what's happening between -3 and -2, that we can easily tell where the global max and global min are going to be based on their x values. So x equals -2 has to be our global minimum because that's going to be the lowest value. It can't turn around and go down further because then we would have another critical point, and we were told there's only one critical point. And that means that x equals -3 has to be our global max because that function has to keep going up to the left. Because again, if it were to turn around, then we'd have another critical point, which we don't. So we're able to discern where our global max and our global min are using what we know about the first and second derivative and local maxes and mins to get a sketch of our graph, and then we can hone in on our interval to determine the global values. Let's take a look at another example. Example 5. Given the graph of f of x below, find the global maximum and minimum for the following intervals. A, x between -1 and +1.5. So here, if we're considering the first interval, that's the entire graph. So the entire graph goes from -1 to +1.5. So if we're looking for the global max and the global min, we're looking for the highest and lowest points on the graph. So the highest point appears to be right here. And the lowest point appears to be right over here. So now I need to find their corresponding y values. So here, this highest point appears to happen at y equals 1.6. So remember, these intervals are counting by 0.2. So we have 1, 1.2, 1.4, 1.6. So I would say here that the global max is 1.6 and the global minimum, if you look here, is going to be at 0. So that happens at y equals 0. Part B, x between 0 and 1. So if we're looking between 0 and 1, that means we're only considering the part of the graph between 0 and 1. So I'm going to trace that in blue so we can see what we're looking at here. So now, if we're considering the global max and the global min on that restricted interval, the global max, the highest point, appears to happen twice at both of the endpoints here. And the global minimum happens to be right about there. So the global max here, or the y value, that's the highest y value, is going to be 1 on this interval, because on this interval it only goes as high as 1. And the global minimum appears to be at 0.8. So it doesn't go up quite as high. And again, these intervals are counting by 0.2. Part C. For the third interval, we're considering what's happening from negative 0.5, which is roughly here, until positive 0.5, which is roughly here. So if we're considering this part of the function, we'll get rid of the rest of it that we're not looking at. Ignore all that other stuff outside of this. We want to find the highest value and the lowest value. So the highest value, again, appears to be at roughly at 1.6. So the maximum here on this interval, the red part you can still see, is about here, which we said was 1.6. The global minimum is the lowest point on this function, so that's actually going to happen around here because it starts to increase, and we said that that happens at roughly 0.8. So again, if you have a restricted interval, you're just looking for the highest and lowest point on that interval, and you're defining it by the y value. Let's look at one more example. Example 6. Just a quick word of warning. This particular example is very heavy on the algebra, so if you haven't brushed up on your exponential and logarithmic rules for algebra, those are going to come back here. So you may need to review those separately if you're not following what's happening algebraically at the end of this problem. For time t greater than or equal to 0 in days, the rate at which photosynthesis takes place in a leaf of a plant, represented by the rate at which oxygen is produced, is approximated by P of t equals 100 times e to the negative 0.02t minus e to the negative 0.1t. When is photosynthesis occurring fastest, and what is that rate? So since this function represents the rate at which photosynthesis is occurring, if we're looking for the fastest rate, we're looking for the maximum of this function. So not only are we looking for the maximum in terms of the global maximum, so the actual rate that's the largest, but also when it's happening. So we need both the independent and dependent value once we've found our maximum. So here, again, we're going to start by finding our first derivative to identify any critical points. So here, my first derivative of this function, I'm going to have a 100 on the outside from my constant multiple rule. Now here, I'm going to have to do a chain rule where my z is negative 0.02t, so my dz dt is negative 0.02. So the derivative here is negative 0.02 e to the negative 0.02t minus, and then again, I have to do another chain rule for my second term where z is negative 0.01t. So my dz dt is just negative 0.1. So minus negative 0.1 e to the negative 0.1t. So my first derivative looks like this. Notice that this is a negative and this is a minus, so those can cancel. So to make my algebra a little bit easier, I'm going to multiply this 100 through to both terms. So that tells me that my derivative is going to be negative 2 e to the negative 0.02t plus 10 e to the negative 0.1t. And I want to know, when does that equal 0? Now here, I notice that I cannot factor out the e term because it doesn't have the same power. If both of these terms had been e to the t with the same constant in front, then I could factor it out. However, because they have different powers, I can't factor it. So now I need to use some algebra to try to solve for t. So I know that eventually I'm going to have to take natural logs to get that t out of the power. But the way it currently stands, I can't use natural logs. First, because the first term is negative, and natural log is not defined for negative numbers, but also because I can't just start taking the natural log until I have a single term with a single variable. So what I want to do here is I want to add the first term over to the right. Doing so is going to give me 10e to the negative 0.1t equals 2e to the negative 0.02t. Now, I want to try to combine like terms. So what I'm going to do is I'm going to divide both sides by 2. That's going to simplify my constants. In doing that, I'm going to get 5 e to the negative 0.1t equals e to the negative 0.02t. Now, I'm going to divide both sides by this e term. So e to the negative 0.1t and e to the negative 0.1t. On the left, it will cancel, leaving me with just a 5. Now, on the right, I need to use an algebra rule. If you have the ratio of two functions that have the same base, which I have here, then I can subtract their powers and write them with a single base. So the single base that I have in both is e, and I'm going to take the top power minus the bottom power. So negative 0.02t minus negative 0.1t. The negatives are going to cancel, and this is going to result in 0.8t when I simplify that. So that means I can write the ratio of this function as e to the 0.8t. So I needed to use this algebra fact in order to simplify this enough where it's now at the point where I can use natural logs. So here, if I take the natural log of one side, I have to take the natural log of both sides. So the natural log of 5 equals the natural log of e to the 0.8t. Again, one of my natural log rules is if you take the natural log of something raised to a power, you can bring that power out front. So I'm going to rewrite this as 0.8t times the natural log of e. But remember, the natural log of e just equals 1, and anything times 1 is just itself. So now I can divide both sides by 0.8. That leaves me with my final answer here of t equals the natural log of 5 divided by 0.8. So that's my critical point. That's the value of t, which is going to make the first derivative equal to 0. Now, at this point, I don't know if that's the point that I need. So I know that my restriction was that time had to be greater than or equal to 0. But if I were to graph the original function, I'd be able to determine if my critical point was a maximum or a minimum. So if you were to graph the original function on a calculator or on a computer, you're going to get something that looks like this. So you can see that your critical point is going to have to be a maximum. So now I know the when. When is the photosynthesis occurring the fastest? At t equals the natural log of 5 divided by 0.8. However, I also want to know what that rate is. So I have to go back up and find the corresponding dependent value. So again, I'd found my critical point to be t equals the natural log of 5 divided by 0.8. That answers the first part of the question. When is the photosynthesis occurring the fastest? That gave me the independent value. But I also want to know what is that rate, that fastest rate that I can achieve. So I need to take this and I need to plug this back into my function. So if I do p of the natural log of 5 divided by 0.8, and I crunch that number, that's going to give me 14.27. So that is the global maximum. That is the largest rate that this can be achieved from this function. So here again, I was able to find the global maximum, and I can do that using what I've learned from this section.